Hello students, welcome to another interesting video. So in this video, we are going to deal with matter waves. It's a very interesting title, right? Matter waves. It's not only interesting, it is important even for your upcoming competitive examinations as well as board exams. So concentrate here. The moment we talk about the matter, we think of particles, matter in any form, either solid, liquid or gaseous state. We think of the particles, either atoms or molecules of the matter. But see, the title, matter is followed by waves. See, these two are two different aspects, isn't it? Matter contains particles. If these particles are moving with certain velocity, they possess momentum. On the other hand, we have waves that represents the wave nature of the radiation. So in this video, we are going to deal with this particle nature as well as wave nature in detail. And let's have a look at some questions also based on these matter waves. Please be ready with your pen and paper. See here, matter waves deals with the dual nature exhibited by the radiation. See, radiation at times it acts as particles and at times it acts as waves. So it exhibits dual nature. Not only that radiation, even material particles like electrons, protons and neutrons also exhibit this wave nature as well as particle nature, the dual nature under suitable circumstances. Louis de Broglie established the relationship between the particle nature in terms of its momentum and the wave nature in terms of its wavelength, giving an equation known as de Broglie's equation. So de Broglie's wave equation is simply lambda equal to h by p. Lambda is equal to h by p. In this, lambda is the wavelength associated with the wave and p is the momentum associated with the particles. Right? H is a constant known as Planck's constant, whose value is 6.625 into 10 power minus 34 in SI units. Those SI units are joule second. So H is the Planck's constant, P is the momentum of the particle, whereas lambda is the wavelength associated with that. Okay, so de Broglie's equation relates the wave aspect, that is lambda on the left side, and the particle aspect in terms of its momentum p on the right side of the equation. Now coming to the derivation of this de Broglie's equation, let us consider energy of the photon as E, which is given by h nu. If m represents the mass of this photon mass is m, the dynamic mass. Anyway, rest mass of the photon is 0. Now, if photon has dynamic mass m, according to the Einstein's mass energy equivalence, the energy of the photon is given by mc square, and it is equal to h nu. So using these two, h nu is equal to mc square. I'll write mc square as mc into c. M into c, mass into speed of light. C is the speed of light. So mass into velocity, that gives momentum. P into c it is. That is h nu. And using the relation c is equal to nu lambda, here nu is equal to c by lambda. Using that, h into c by lambda is equal to p into c. Now you can cancel c on both sides. You are left with h by lambda is equal to p. So this is what is the de Broglie's equation. Or rearranging, you'll get lambda is equal to h by p. Hope that is clear. Lambda equal to h by p. Understood? Right. So using the relation E equal to h nu and equating it to mc square, we get p equal to h by lambda or lambda equal to h by p. Now, what is the wavelength associated with a body of mass 1 gram moving with a velocity just 1 meter per second. See, mass is 1 gram. It's a body of mass 1 gram moving with a velocity 1 meter per second. Now taking 1 gram in SI units, it becomes 10 power minus 3 in kg. Using the de Broglie's wave equation, lambda equal to h by p. That means lambda is equal to h by m into v. Now v is anyway 1 unit. This velocity is 1 unit. Mass is 10 power minus 3. Substituting the values of h and m, as v is anyway 1 unit, 6.625 into 10 power minus 34 is the h value by mass 10 power minus 3. That comes out to be 6.625 into 10 power minus 31 meter. See, this value 10 power minus 31 meter is very, very small, right? So the wavelength associated with a particle moving with a velocity 1 meter per second, if the particle mass is 1 gram or even if it is 1 kg, that becomes very, very less, significantly small value. Okay, so wavelength associated with the bodies is very, very less, de Broglie's wavelength. Now, what is the de Broglie wavelength of an electron? See, if m is the mass of the electron, E is the charge of the electron. If it is accelerated by a potential v, then it attains a velocity v, right? Now, its kinetic energy half mv square can be given as EV from work energy theorem. Change in kinetic energy is equal to work done. Now, this kinetic energy can be expressed in terms of momentum. K is p square by 2m from mechanics. That is equal to EV. Then what is momentum p? It's 2mev, where v is the accelerating potential. Once you know the momentum, you can find the de Broglie wavelength associated with the electron as lambda equal to h by p. So, sorry, p is root 2mev. P square is 2mev here. P is root 2mev. So, lambda comes out to be h by root 2mev. See, in this, except v, remaining all are known values. H is a Planck's constant, that value we know. 2 is a constant. M is mass of electron. E is charge of electron, that value is also known. The remaining is v. Keeping this root v as it is, substituting all other values, it comes out to be 12.27 by root v. V as it is, accelerating potential. Simplification of the remaining values gives you 12.27 in angstrom unit. Applying whole root, see, if you square this numerator 12.27, its square is almost equal to 150. So in those terms, you can write lambda as whole root of 150 by v in angstrom. That is the wavelength associated with an electron accelerated by a potential v. Now you need to substitute only v value. Substitute v value and simplify it. Directly you will get the wavelength in angstrom unit. Understood? So that is the de Broglie wavelength of an electron. Now if you talk about the de Broglie wavelength of a proton, same equation will work. This equation will work even for a proton. Only thing is, instead of mass of electron, you will have to take mass of proton. In place of mass of electron, we will have to substitute mass of proton. Only m changes here. Charge is same for electron as well as proton. Only varying factor is m. By substituting suitable value, that is mass of proton, you can find the wavelength associated with the proton. Okay. Now, see, the de Broglie wavelength of an electron is lambda is equal to root 150 by v in angstrom. Similarly, the de Broglie wavelength of a proton, if proton mass is substituted instead of electron mass in this equation, we'll get it as 0.286 by root V in angstrom unit. You need to remember these values. Lambda of proton is 0.286 by root V in angstrom. Same way, even for a gaseous molecule, what is the de Broglie wavelength of a gas molecule? See, considering a gas molecule at an absolute temperature T, its kinetic energy is given by kinetic energy is 3 by 2 kT. Now, using the relation P is equal to root 2m times kinetic energy, this is the relation between momentum and kinetic energy. Substitute kinetic energy, it's root 2m times kinetic energy, that is 3 by 2 kT. Now, 2 and 2 gets cancelled. You are left with root 3m kT. That is momentum. Once you know momentum, you can find the de Broglie wavelength. So, lambda of gas molecule is h by root 3m kT. Clear? Another one. De Broglie wavelength of a neutron. If you know the neutron energy, use neutron energy in electron volt, then lambda of neutron is same as proton 0.286, but denominator is energy, root of energy in electron volt, 0.286 by root energy of the neutron in electron volt, and this lambda is expressed in angstrom unit. That is for neutron. Now for alpha particle, de Broglie wavelength of an alpha particle is 0.101 by root V angstrom. Alpha particle. Next one is deuteron. It's 2 times this alpha particle value. Lambda of deuteron is 0.202 by root V angstrom units. So these are all important relations. Please try to remember these. De Broglie wavelengths of electron, proton, alpha particle, deuteron. Okay. Now, another important aspect, that is Bohr's second postulate. You know what is Bohr's second postulate? It is about the quantization of angular momentum. See, for an electron revolving around the nucleus in a particular orbit, nth orbit, that electron acts as a wave of wavelength lambda, which is given by h by p. Okay. Now this wave acts as a stationary wave, as shown here. It looks like a stationary wave of some fixed wavelengths. Integral multiple of lambda is the total length of the path. Since it acts as a stationary wave on a string, the length of the path is always an integral multiple of wavelength. That becomes n times lambda, where n is an integer. Understood? Right. If length of the path is n lambda, what is the length of the path according to this figure? If r is the radius, length of the path is nothing but its circumference, 2 pi r. So for an electron in nth orbit, 2 pi r n, radius of nth orbit, is n lambda. What is lambda? It's h by p or h by mv. So n lambda would become n into, for lambda you can write h by mv, isn't it? Now rearranging this, mvr comes out to be nh by 2 pi. mvr is equal to nh by 2 pi, where mvr is nothing but the angular momentum. Angular momentum is an integral multiple n times h by 2 pi. It is integral multiple of h by 2 pi. That's what is the second postulate, isn't it? Bohr's postulate. So this is the angular momentum condition proposed by Niels Bohr. Understood? Right. So for more such interesting videos to enhance your subject knowledge, you can subscribe to the channel Time for IIT JEE NEET. Now let's have a look at some questions based on these matter waves, the de Broglie concept. This is a question that appeared in recent JEE entrance, JEE main. An electron with mass m with an initial velocity v is v naught I cap, means it is along the positive x-axis where v naught is greater than 0, enters a magnetic field B, which is b naught j cap. Magnetic field is directed along the y-axis. If the initial de Broglie wavelength at t equal to 0 is lambda naught, then the value after t would be, what will be the wavelength after a time t? See, question seems to be lengthy and twisting, but if you observe this scenario, when an electron enters a magnetic field, the magnetic field doesn't do any work in this. That means speed of the electron remains same. As long as the speed is same, its momentum remains same. If momentum is same, is there any change in wavelength? We have lambda equal to h by p. As long as this part is constant, lambda will remain constant, right? So, it's lambda naught. Even after a time t, the value will remain lambda naught. Understood? Such a simple thing it is. Let us see another question. A subatomic particle of mass 10 power minus 30 kg is moving with a velocity 2.21 into 10 power 6 meter per second. Under the matter wave consideration, the particle will behave closely like X-ray, infrared radiation, gamma rays, visible radiation. So you need to find the wavelength using de Broglie's concept. Once if you know the wavelength, that wavelength belongs to which of these four? That's what we have to check. Now, using de Broglie's relation, lambda is equal to h by p, that is h by mv, isn't it? H is given 6.63 into 10 raised to minus 34 in SI units by mass 10 power minus 30 into velocity 2.21 into 10 power 6. Okay, now 2.21 cancels 6.63 3 times. The remaining part, it is 10 power minus 10 in meter. Or this can be written as 0.3 into 10 power minus 9 meter. 10 power minus 9 meter is nothing but nanometer. So 0.3 nanometer is the wavelength of which of these radiations? That is clearly X-rays. Because for X-rays, the wavelength ranges from 0.01 nanometer to 10 nanometer. This is the wavelength range of X-rays. Now 0.3 nanometer is falling within this range. So clearly it is X-ray. Okay. Next. The de Broglie wavelength. This is another question from your recent JEE entrance. The de Broglie wavelength associated with an electron and a proton were calculated by accelerating them through same potential difference. Same potential of 100 volt. So accelerating potential is same for two different particles, that is electron and proton. What should nearly be the ratio of their wavelengths? Mass of proton and mass of electron are given. See, already we have a simplified value for the wavelength of electron, which is 12.27 by root v in angstrom, and a lambda of proton, that is 0.286 by root v angstrom. In both cases, v is same, 100 volt. So root v gets cancelled if you divide these two, and we are asked to find that ratio, right? It is wavelength ratio of first particle given is electron and the second one is proton. Electron, proton, same order we have taken. No need to substitute these masses again. So root v and root v gets cancelled. You are left with 12.27 by 0.286. This is almost equal to 43. So 43:1 is the correct answer for this question. Understood? Yes. Now, for any enquiries regarding online coaching or classroom coaching, you can visit your nearest T.I.M.E center or log into our website www.timeforeducation.com. Now continuing with this questions based on de Broglie's concept. This is the question that appeared in recent NEET entrance. De Broglie wavelength of an electron orbiting in the n equal to 2 state of hydrogen atom is close to. Its Bose radius is given as 0.052 nanometer. See, n equal to 2 is the state of the hydrogen atom given. Then radius in nth orbit, we have n square times r naught, the Bohr's radius, that is 4 into 0.052, which comes out to be 0.208 nanometer. Okay. Now, this is for an electron orbiting around the nucleus. For an electron, we have MVR is NH by 2 pi. Here n value is 2, so 2 and 2 gets cancelled. Now, we have to find de Broglie wavelength. What is de Broglie wavelength? Lambda is equal to h by mv. Rearranging, what is h by mv from the above equation? It's pi times r. Pi is 3.14 into r, that is 0.208 in nanometer. So this product comes out to be 0.67 in nanometer. 0.67 nanometer is there in option D. So correct answer for this question is option D. Another question from the recent NEET. A photon and an electron, it's not a proton, it's a photon and an electron mass is m, have the same energy, their energies are same. The ratio of their de Broglie wavelengths is lambda of photon to lambda of electron. See, for a photon, we have energy E is equal to h nu, or it is hc by lambda. So from this, what is lambda of photon? Lambda of photon it is. So it is hc by E. When it comes to electron, on the other hand, we have P of the electron is root 2m times its energy, because both these particles have same energy. Then wavelength lambda is h by p, h by root 2m times its energy. This is for electron. Now, question is about lambda of photon to lambda of electron. Photon is hc by E by h by root 2m times E. So that simplification gives you C into root 2m by E. C into root 2m by E is here in option A. So that is the way to handle these questions, and you can easily handle these questions if you are good at the basics. So for strong basics, you can subscribe our channel. So with that, I would like to conclude this video. Thank you very much for watching. See you in the next video.